Okay, so thank you for staying here, even with this nice weather now. But for us, it will rain like yesterday, I don't know. Okay, so I will go to the next subject on these multimode things, which is, of course, when you have this very complicated system made of a lot of different directions, different frequencies, different polarization. Okay, so multimode field. I don't know how to, something like that, okay? Not just a beam, like really. How to measure these properties? Of course, what you have first is a detector. So you put your detector somewhere, okay? Your photo detector, the photon counter, whatever. And then you expect to have some information about the system. So this is my part, it's fourth part, which is measurement on multimode states. And the first thing to do, of course, is just that is to what we can call a direct detection. So if you have a small detector, very small, staying at a point R, within a small value delta R around it, okay, small area, and which registers will record the information at just at time t, also with some time window delta t around that. So Roy Glauber, at this place again, 50 years ago, taught us that this kind of thing gives information about an operator that I will call n, number of photons measured at the point R in time t, which is nothing but E minus, which is E plus dagger of R and T, E plus of R and T. Okay, so this is something, it's a square of the field in some way. Classical equivalent of that, of course, is the modulus square of the complex field. Makes sense? So what Roy Glauber showed was that by a perturbative calculation of the quantum aspects of photoionization, okay, so you send light on atom and then it delivers an electron that you measure, so this is photon counting. Then what he showed was that the signal is proportional to this quantity, okay, to the mean of this quantity. And then it was showed later that if you use detectors with quantum efficiency 1, so which exists or close to 1, then not only the mean is proportional, the mean of the number of excitation which is recorded is proportional to the mean of that in the quantum state, but this kind of operator is useful not only for the mean, but for the variances, the correlations, and all possible measurements that you can do with that. So you have access to the observable N. Okay, so if I use my field expression, it is sum over M of some basis. So I take M, Bm, so I take this one, Fm of R and T. Okay, so what I used before. Then if you put that in the expression, you find that, for example, the mean of N, of R and T, but it will be the same for the other, is a sum over M and M prime. Okay, you have this double sum coming from the double term. Then you will have B coming from this one and B dagger coming from the other. So you will have B dagger M prime, Bm in the mean quantum mean here, and F conjugate M
prime of R and T, Fm of R and T.
So it's a rather complicated expression, which involves at the same time a combination of these elements of this covariance matrix, okay, in terms of the B's, and a combination of the spatial and temporal variation of the field at this point. Okay, but here also you have, it's kind of product of two covariance matrices, the quantum one here, and the classical one here, so the optical one here. Okay. So things are, so it's complicated, okay? It gives a kind of global expression depending on a lot of parameters of the states. So we need to do better in order to have an information that one can use. The simplest thing is to have a detector of broad area plus long averaging times. Okay, so what you will be sensitive to then will be to n, which will be an integral over d2r dt. And okay, so let me precise a little bit more. So my field is propagating mostly in the z direction, okay? And what I use is a detector which is large enough so that it integrates all the field in the transverse direction. So my integration here is dx dy, and then it's a dt. But what is time? Time is propagation along z. I have z called ct. Okay, so my dt here is dz over c. Okay, because the field is propagating in this direction of the previous one, of R and T. Okay, so then as far as the coordinates are concerned, they are only here, this part of the expression. And you see that then I have to integrate this kind of thing. So yeah, I'm back to the scalar product of modes. Okay, so I can then use the fact that this is delta m prime. This is orthonormal. So in this case, this is delta m prime, and what I have access to is just b dagger m bm. Okay, in terms of operators. And this is nice because, as we have shown yesterday, this quantity is mode independent. Is intrinsic. So at least I measure something which is intrinsic by doing that, which is kind of global information on the total number of photons present in the system. Okay, this is the first step. One needs to do better. And to do better, one needs balanced homodyne detection. Okay, so you know, I think, already this kind of trick, which is very useful and based on the beam splitter, very important device in quantum optics. And so here I shine this field, multimode field. Okay, psi, multimode. Okay, I choose one basis, for example, the Fm basis of mode to describe it. Okay. And then I have a beam splitter, and I have two detectors that do that kind of thing, so that I are able to measure all the field. So of course, you don't need for that to have a detector which spans over the whole universe, transverse plane. So just broad enough so that you take all the intensity. So, and it's vacuum around. The same in time. You take all the, if it is a pulse, you take the whole pulse. With it, it's enough. Okay, and this kind of thing
sometimes are called bucket detectors. Buckets. Bucket is a sew. Okay, so you take all the information. Okay, so you have two bucket detectors here. You have photocurrent, which is proportional to number of excitation. Then you multiply by number of electrons to have the real current. Because here, because of quantum efficiency 1, every photon transfers into one electron. And you make the difference. You have a signal that I call n minus here. So here, now you have to put something on the other side, which is called the local oscillator. So what we will put here is a local oscillator, that is to say a coherent state, so a laser, that I will write in the form alpha, the usual expression of a coherent state, as A amplitude and phi the phase. And I put it in some mode, of course, and the mode I take is the first one of the bases, for example. So it's a single mode coherent state. We know that any coherent states are single modes, but okay, I choose this mode. Okay, so I will not go into the detail of the calculation. Also, it's everywhere. So you have to transfer the operators, annihilation operators of a mode here into the annihilation operators of the mode at the output of the beam splitter using the expression, input-output expression of the beam splitter, which is well known. And then you take this kind of thing here, same on the other one, and you make difference. Okay. And the important fact is this balance thing. Balance means that you take the two and make the difference. Okay. And in this process of making the difference, a lot of terms cancel. And n minus at the end of that is found to be B dagger so sum over n m, let's say, of B dagger m B prime m plus B m B dagger m. Here. What are the B and the B? The B and the B prime. So the B are the bases here, okay, the BM on this side. Okay, they allow us to describe the field on this side. And the B prime are here. So the B prime correspond to F prime modes, which are the mirror modes of this one. So the one which will mix on the beam splitter. Okay. So it's the same. In order to have the F prime, you just take the mirror image of the other one. Okay, nice expression. It's a bilinear combination of the B and B daggers of the two inputs. Okay. And now I take use the fact that I take this in mean, meaning that I have to take the mean in the state, input state. Input state is formed of this part and this part. Okay. So it will be psi for the one part and a to the I phi for the other part. Psi, a to the I phi. Okay, so the psi you don't know exactly what it is, but you know more on a to the I phi. So if you a to the I phi as a mean gives a 0 for, so it's B prime. It's on the prime side, on the other local oscillator side. B prime acting on modes which are not F1 are vacuum modes. Okay, so it will give 0. So B prime a to the I phi is delta M1, okay? When it acts on something else than the mode coherent state, you find 0. 0, not delta M, not 1. 0 if M is different from 1, and it will be a to the I phi, a to the I phi, because it's a coherent state, if m is 1. So it removes a lot of all terms here, because you apply it on this side for this one, and no, sorry, the reverse. This one you apply it on the right here, it gives 0, and this one you apply it on the left and gives 0 also. So at the end of all that, it means that the mean of n minus will be a in front of it, and then you will have no longer a sum, just one term, which will be b dagger 1 e to the I phi plus b1 e to the minus I phi, because I apply it on the other side in psi. Okay, so this way allows us to measure the mean of the operator b, that we can call b. What is my name? x1 phi. And this one is well known. For phi equal to 0, I have b plus b dagger, it is x1. And phi equals to pi over 2, I have I and minus I. So it's I, it's what I call y1, okay? The quadrature operators. So the homodyne detection allows us first to measure the quadrature operators, the ones which are very important and the ones which do not commute, so they have a lot of quantum effects associated with that. And then on one only, okay? At the beginning I had a sum, but the single mode character of the local oscillator just eliminates all the other terms. And so the homodyne detection in some way is a projection. Okay, so this is homodyne detection projects on local oscillator mode, if it is single mode. Of course, if it is not single mode, then you have different terms in the sum. Okay, so this is very important and very nice. You have access to all the components. If then, after a first measurement with F1, then you go to F2, second measurement with F2, with F3, F4, and by scanning all the possible, not all, of course, but sufficient number of modes of a given basis, then you have a lot of information. Okay, this is for mean. And mean values are not so interesting. It's more the variances, the covariances, and things like that. So it is, I will not go to the calculation here also, but you can show that the variance of this quantity is equal to a squared, the variance of x1 phi. But there is another term, additional term, which is psi and dot, this one, n psi. Okay, so the variance is the sum of two terms, one depending on what I want. Okay, this is the variance of my operator, quadrature operator, multiplied by the amplitude, by the energy, because the squared, by the energy of the local oscillator. Very nice. I have an amplification process built in. Okay, so the more light, the more power I put here, the better the detection of the squeezed components and these very little things at the level of quantum fluctuations. They are promoted by a squared. So this is another advantage of homodyne detection, this amplification. But then there is this term. This term is the energy of the multimode state. Okay. So in order to have what I want, okay, only the information about the quadrature, I have to assume that this is small. So it's only when I have a weak field here and a strong one here that I measure the variance of the quadrature. But usually, here you have milliwatts, so a squared is very large, 10 to the 16, something like that. And the other part here is a very weak field, usually around 0, so it's a very few energy, very small energy. Okay? So it's good news. I am able to measure by these techniques all these kind of quantities. Okay, all the variances of my states. But it's not enough. You remember that in the description of multimode fields, you have this diagonal part of the covariance matrix, but then you have the non-diagonal part, which are all the correlations between the different modes in the x, in the y, in the xy. So how to do that? Simple. Then you take now, for correlations, okay, not variances, so you need two modes, because what you want to know is the correlation between the two. So as we take a local oscillator in mode, so if I want to see the F1, F2, for example, correlation of M prime, so I take a local oscillator in mode okay, Fm prime. As you remember, a mode is nothing else than a solution of Maxwell equations. So by superposing two solutions of Maxwell equations, I get another one, okay? For example, if I deal, what I will do later, with frequency modes, okay? Fm is one frequency, Fm prime is another frequency, and this is just a coherent superposition of two frequencies, so it's a bit mode between the two, with some phase that I can adjust, okay? And I send in this mode, and as of here, a coherent state with a phase phi, okay? And if you do that, what you measure is delta squared. So measure, of course, the combination, which will be a bit more complicated than this one, which will be Bm e to the I phi, because it's this term, plus B dagger M e to the minus I phi, okay, this part. But then I will have the second mode, which will give me plus Bm prime. So if I have this one and multiply by e to the I phi, I have just e to the I phi prime, plus B dagger M prime e to the I phi prime minus I phi prime, which is x m phi plus x m prime phi prime. Okay, so I measure something relative to the sum of the two quadrature operators of these two things. And then by looking at the variance of that, I will be sensitive, of course. If I look at variance, that's variance of delta squared of xm phi plus xm prime phi prime. This is what I measure. And you know that you can write this as delta, the variance of x, m phi, plus the variance of x prime, m prime phi prime, plus twice the correlation, the xm phi, xm prime phi prime. Okay, of course, if the two are not correlated, if it is 0, then the variance of the sum is the sum of the variance. This is well known, okay? But if it is not, if this is not equal to the sum, then the difference between the two gives you the value of the correlation between the two. Very simple. So now we have access to everything. This, what you want to see, know, and this for any mode. Okay? So in order to have the whole information, of course, you need to have the whole basis, which is a bit big. But okay, let's take a big enough sample of the basis. Okay, you will see in experiment, we take maximum so far is 16 different modes. And so we need to measure the n mode variances, okay? And then the nm plus nm minus 1 over 2 couples of modes, which give, by this kind of thing, the variances. So total number of measurements is nm plus 1 over 2, okay? So it's a lot when if you want, but It's what you need, of course, in order to fill all these big covariance matrix by experimental numbers. You will see what we have done. So it's okay, it's good. It gives all the fluctuations are Gaussian, which is the case for many instances, many experiments. Then all the information is in the variance, the mean also, but the mean, okay, it's simple to measure, but all the information about quantum noise is on the variance. The other higher order correlations are functions of variance, okay? So you have the total information in this case. If this is not a Gaussian state, then you need more information in order to have the total information about the state. In this case, you need to scan phi and phi prime, not just the 0 and pi over 2, but all the values of phi and all the values of phi prime. And this enables you to reconstruct the full Wigner function of the system. So it's even bigger, of course, because you have to make all the coupled phi prime with a large enough number of phi and large enough number of phi prime. So it's a lot of work. Okay, but it's possible. So by this way, one is able to know everything about a multimode quantum state. But it's very long. So there is a technique which is a bit faster, not a bit, which is much faster. Okay. Remove this part, which is 4.3, the multipixel homodyne detection. Okay, what do you do? Instead of sending your state psi here and local oscillator here on the beam splitter, okay, you do a bit more. So on this way, you separate the modes. For example, here also, in the same way. I will go back to the way to separate modes, of course. Then you measure in different way the different modes, and you make the difference mode by mode. Okay. So I've written here, I've drawn in for 3 modes. Experimentally, we have done that for 16 modes. So it's a lot of wires. It's bigger and bigger, but it's possible. Okay, so how to separate modes? So it depends on which mode you are interested in and which mode it is simple or not to do it. The simplest thing is to separate the pixel modes. Okay, you just take an array or CCD camera here, and then you have the pixel basis, which is readily separable or already separated. So this is the way it has been done for the first times in this kind of scheme. But of course, if you put a grating or a prism here and here, okay, your grating has dispersion and gives the different frequency modes and are separated in space, and then with a CCD camera or whatever, or an array of detectors, that will then you measure frequency components, okay? What I call this Frexel or, okay, frequency components. This is what we will do in the experiment later. Okay, so here also I don't make the calculation, just give you the result, simple. Okay, I'll keep that. It can be in time also, okay? You can have a single detector, but then take, it's what was done in the experiment of Olivier Morin last time. So there was a single channel on both sides, but then it was cut in time. Okay, the different time slots were recorded. So in the mth output, okay, m is this one. The n minus m, so what goes out here, operator is am bm plus am. So with always a e to the I phi present, bm dagger e to the minus I phi. So I could have put am in front. So you recognize that one is able to have access as expected. Of course, since we filter the mode, we have access to the quadrature operator of the corresponding mode. Okay, and what is in front of it? It's am is the equivalent of a here. Am is a component of the local oscillator on the mode fm. So am is the integral of this here of f. So I didn't put it his name. Here I can call it, what is the name I took? G0. Okay, it has some shape that I call G0 of R and T. And this one is G0 of R and T Fm star. Okay, the projection of the local oscillator mode onto the mode which is filtered by the detection. Makes sense, okay? So if you want to have the best measurement, so you need an AM which is the same almost in all the different modes. So you need a mode that spans equally over all the bases that you can take, kind of plane wave thing. But if you know AM, it's good. If AM is not too small, then you can extract it from this kind of thing. So what is interesting is that in a single shot, you have a lot of information. So sorry, what kind of information do you have? Of course, you have the variance of the quantity, just looking at the fluctuations of this NM, but how about the correlations? Correlations is very simple because, for example, M prime here, you have fluctuations here that you record in time. You have fluctuations here. You make the product at the same time, and you average this product. So you use just the definition of correlation, mean of the product. And you can do it online because you have all this information coming at the same time on the different wires. So it's very fast because you have everything at the same time. So it's much better than the other one. But it will not measure everything. You see here, you measure a given phase because you put a given phase on the local oscillator. And you are not able to measure at the same time the result with phi equal to 0 and phi equal to pi over 2. You have to choose one or the other. So by this thing, on a single shot, you will measure a part, 1/4 of the real covariance matrix. Okay, but it can be enough for a lot of applications. If you want to have the total thing, then of course you change your local oscillator with different phases, but you have to change the local oscillator phase in a way which will change, not a global way. Otherwise, you will have these two parts, but not the XY component. You need to modify the phase just on AM and not AM prime. Okay, so it's a bit complicated, but it can be done to change the phase only on one component of the local oscillator. That is possible. Okay, so I have access to a lot of information, even the total information on my state. If I use this one, long but complete thing, okay. This one faster, but only a part of the information. For the experiment, this one was for 10 different modes, half an hour measurement. millisecond. So it's a big difference. Okay, my last part on before I go to the experiments is the generation of these multimode things. Of course, now I'm ready to measure them, but I have to produce them. So this part is 5, generation of multimode non-classical states. So what is the connection of this series of lectures with the summer school here, the spring school here? It is now, because what you need for generating multimode state is nonlinear optics. Okay, so you take a box, you put a lot of things inside, of course, but mainly you have nonlinear optics inside. Chi2 mainly, so it's good, parametric effects. Chi3 for a lot of other possibilities, or even more complicated nonlinear effect like saturation of two-level systems and things like that. Okay? So these things are input and output. So I have an in and an out. Okay? And so I have here a basis on which I send light into the system on the different modes, for example, different directions, or different frequencies in parametric down conversion of different frequency generation, second harmonic, all that kind of thing. Okay, so here I have a basis that of creation operator, annihilation operator that I call AI in. Okay, so a series of I values which enable me to write the state of the light at the input. What do I put at the input? Laser, okay, so that is to say coherent states, and vacuum. I send nothing, but nothing means that I send vacuum states. Even if I don't want to do it, the vacuum is here. So, and at the output, there is some light in the modes, and so they are the same modes, but now they have been processed by the nonlinear effect, and they are described at the output, but new values that I can span on these parts. Okay, so there is a relation between this and this, which depends on what you have put in the middle, of course. So you have an AJ out operator, which is a big function that I will call f of what you have put at the input. AI in. So I have not closed the bracket here. Why? Because so A is a bit like field, okay? E plus. E plus is a linear combination of it. So for a lot of experiments, a lot of instances, the transformation F, quantum transformation F, looks not almost the same as the classical transformation of the field. Okay, for example, for the beam, if you put here a beam splitter, it's linear optics but non-linear optics. Okay, the transformation for the A's is the same as the transformation for the classical field. If you put a parametric device here, it's the same also, let's say. Okay, but if you remember what is the transformation, the classical transformation of field in a parametric down conversion, for example, okay, from classical nonlinear equations of propagation, you remember that there is a star somewhere. Okay, the output field depends on the complex conjugate of the input for some part of the field. Okay, so here it means that also, so it will depend on all the I component, but also on the quantum equivalent of the star, which is a dagger, okay? One dagger in, I dagger in, okay? This transformation is not always the same as the classical one. For example, for just an amplifier, or it's not the same. Okay? So how to find F? You have to make a model of a quantum model of what is here, or you can guess more or less precisely what is the transformation. And you have a guide for that. The guide is that this is an output field. Okay, this goes out in vacuum, nothing after. So it means that it has to fulfill the constraints of a free field, meaning that Aj out, Aj prime dagger out must be delta J prime. Delta J prime. So whatever the transformation you put here, you have to check that it preserves commutation relation. Okay, what is called a canonical transformation, preserving. But you remember symplectic things last time? Symplectic means canonical, so preserving commutation relation, plus linear. So is it linear here? It depends, okay? But very often you can have a small fluctuation approximation. What does it mean? It means that if you consider the fluctuations of this quantity, that is to say the difference between I in and the mean of it, okay, this is the difference between the value that you measure here and the mean, so it's just the fluctuating part of the thing, so that I can call delta AI in. Okay, you assume that all the matrix elements of this operator are small if, okay, mean, but not only mean, is much smaller than the mean. So let's say the Aj in. Then it's possible to make a first order expansion of this kind of thing, okay? And you will have then an expression which will be linear in fluctuations, okay? In this case, you will have delta Aj out, so I remove everywhere the mean, which will be a sum of Fij, some value depending on derivative Ai in, delta Ai in, plus sum of J, Ij, sum of I, delta A in dagger. Okay, so when you deal with nonlinear optics, in order to have an effect which is not negligible, you need to put some power on the laser, okay? And in this case, this is true, okay? No problem. This is very, very good approximation. Actually, some people would like to break this approximation because then you can have other kinds of non-classical states of light, and nobody succeeded so far. You need that you have to make nonlinear effects at the photon level, single photon level, which is very difficult. You can do that with nonlinearities which are bigger, for example, the one associated with two-level atoms, saturation of two-level atoms, something like that. But the non-resonant ones that are the ones of nonlinear optics are really in this approximation. Good. So what is this transformation? It's a symplectic transformation. Okay. So I can use, like I did last time, but in a more detailed way now, because this is a general symplectic transformation now. It's not the subgroup of unitary ones. For the unitary ones, you had only this part. Okay, remember? You had no mixing between A and A daggers. Here you have. Okay, so what are the properties which are interesting? This one is, so it's, this I will write it in a way which is, okay, A out is equal to S A in. Okay, so this is the column vector of the delta A, this one, okay, including the A's and the A daggers. So it's a 2n column vector, okay, where n is the number of modes. And it is related with the matrix, because this is a matrix, with the 2n input thing. Okay, so S is a symplectic transformation as a form of a 2n by 2n matrix. I will not go into the details. Of course, the fact that this transformation preserves the commutation relation gives a lot of constraints to S. Okay, I will not go into all that. But what is interesting is what is called the Euler decomposition, which tells you that any S, any symplectic transformation can be written in a simpler way. The simpler way is a unitary transformation 1, a diagonal part D, and another unitary transformation. Okay, so this can be written for any S, and it's not the way to write it is not unique. So U1 and U2 are unitaries. So, and you know that unitaries are the same as modes basis change. Okay, even if it's not, it can be a real transformation. And D is a diagonal. D is a diagonal matrix which contains terms which are e to the R1, e to the Rn for the first half of the matrix, and e to the minus R1, e to the minus Rn for the second. Okay, so the covariance S matrix is always divided in four parts, because this is the A part and the A dagger parts, A part and the A dagger parts. So I have e to the R here and e to the minus R here. Okay, so I multiply the X components by e to the R. I multiply the Y component by e to the minus R, which is inverse. This is a squeezing transformation. Okay, so this is a set of squeezers, of independent squeezers. Okay, so this means that any transformation, like any nonlinear transformation acting on the input mode, can be reduced to squeezing transformation, provided you are in the right basis. Okay, meaning that you change here. So when you apply it here, apply a first transformation. So it's a new set of A's. Okay, so you acting on the A's is a new basis of A's. Then you squeeze this mode, and then you reshuffle everything. You redirect the squeezed quadratures on different modes. So in this case, you not only get squeezing things, but you get quantum correlations, as we will see a bit later also. Okay, so any nonlinear transformation at the quantum level is squeezing in a given basis, well-defined basis, then reparted, divided into on another basis. Okay, so I think it's a good way to see things. So if one starts, if input is vacuum 0 here, vac is a total vacuum where all modes are 0. So is 0 in some modes, alpha in others, meaning that I shine on my nonlinear crystal laser plus nothing. Okay. Then what I do is change that, diagonalize, and make another transformation of that. And as I told you last time, the Wigner function is preserved. The Wigner function shape is preserved in symplectic transformation. Okay, just it changes, the values are not at the same point, but they are the same values. Okay, so what is the Wigner function of the input? It is a Wigner function of vacuum, Wigner function of coherent state is Gaussian. Input, you have a Gaussian Wigner function. But it can be a complicated Gaussian. Okay, it's not a single mode Gaussian thing. It's a Gaussian thing in all the variables alpha 1, alpha 2, alpha 3, which enable you to describe all the modes. Okay, so it means that it will be a e to the something which is a quadratic form of the alphas. Okay. I have no time to go into the detail, but you see it. Okay, because this thing, which is then transformed by the transformation S. But then it means that at the output, you will have also Gaussian wave function. And since the Gaussian has no negative values here, it will have no negative values here. No, positive Wigner. So does it mean that it's not, is it classical? So this is a big debate. But for example, if you say that positive Wigner function corresponds to a classical state, then you are obliged to say that vacuum is a classical state, which is not totally true. Okay, the vacuum state has vacuum fluctuations of quantum origin. So let's say that since it is a positive Wigner function, it means that the quantum mean is a bit like a classical mean, because the Wigner function is a real probability distribution. It is always positive. So it means that you can handle the quantum fluctuations of these fields like classical fluctuations. Okay? So the quantum part of the problem is just the input. You start from states which have noise in which you have h bar somewhere. Okay? So if you put h bar equal to 0, you have no fluctuation. So the size of the fluctuations is quantum. Then you process it, you squeeze it, you put it on different modes, and at the end, if it was classical fields, and you have something at the output containing h bar also. Okay, but the way it has been processed is the same as a classical processing of classical fluctuations. Okay. Okay, so we have learned a lot by doing that. We can go a little bit further. Yes, I'm on time. By looking at the covariance matrix, the real covariance matrix. So here it was just the transformation of modes, okay, of the A's. But as you have seen, all the information is in the covariance matrix. So here I take the one which is adapted to this kind of description, in which you have A and A daggers. So you have two NM vectors. So this covariance matrix will be the big one with two NM dimension. Okay, so containing the XX here, the XY correlations here, and the YY correlations here. Okay? So this that I call V. So V of vacuum, what it is. So of course, there's no correlation between the XX in vacuum because it's a circle in a given mode. There are no correlation between vacuum fluctuations in different modes. So this is 0, 0. And so what remains in this case are just the size of the vacuum fluctuations in the diagonal. And the way I've defined my A's and my X is such that it is 1. So vacuum fluctuations are 1 in this kind of thing. So my matrix is 1 for the X component, 1 for the Y components, It's just the identity matrix. Okay, so any departure from identity matrix of the covariance matrix, of the real covariance matrix, this one, is a sign that you have changed things, you have made nonlinear effects, and the fields which are coming from that are not classical. But, for example, if you have a one mode, so let's go back to the simple things. One mode, you have a 2 by 2 matrix, okay? 2n is 2. So you have here delta x squared, delta y squared, and here you have xy conjugate, but it's real, so it's a matrix, okay? So this matrix cannot be anything, as you know, because it deals with variances, and Heisenberg is somewhere, okay, behind that. What does Heisenberg tell us is, so I don't know if you are acquainted to write a Heisenberg inequality with correlations. Usually you don't care about correlations, but there is an extended Heisenberg inequality which tells you that the product of that, so is it plus or minus? I know. What is it? Oops, I lost my page. It's minus the correlation xy squared is bigger than 1 or 2, 1, yes. Okay, this is Heisenberg. So you have different ways to look at it. Of course, since this part is bigger than this part, you can put here smaller than delta x squared, delta y squared, and then you are back to the usual one. You can also, since it is bigger also than 0 here, you can put 0. So if you have this bigger than 0, it means that the product of variances is bigger than the correlation squared, which is a Cauchy-Schwarz inequality. And here you see that it's, if you have a correlation, you can put this on the other term, so it will increase the limit. So when you have correlations, you have more noise in some way, okay? The onset of correlations raises the limit for the product of fluctuations, okay? So it means that a quantum effect can be either seen on correlation, but then it will spoil the squeezing in some way. It will add noise, or it can be seen on noise reduction. But it is the same resource in some way. You can put on reduction of fluctuations or increase of correlation. And the two are related by that. Okay, so this is for one mode, and for n modes, you have to write something a bit more complicated. It is B, the covariance matrix, which is here, plus a matrix which is 0, 0, I. Okay, so I add to my matrix V, this one, a matrix is 0 on the diagonal, so I don't change this part, and I add plus I on all the components here, on the diagonal components here, and minus I here. Okay, and this is a positive matrix, positive operator. Meaning that it has, for example, eigenstates which are all positive. Okay, so you can verify that if you take only one mode, you are back to that. This thing is just the determinant of the matrix. Okay, so a covariance matrix cannot be anything. Okay, it's a physical one, has this kind of constraint. Okay. And the last effect is what is called Williamson theorem. So the last mathematical theorem that we use from symplectic theory, okay? Williamson theorem is a kind of diagonalization theorem for symplectic transformation on the covariance matrix. So you take a given covariance matrix V, so which comes from a given processing in a nonlinear crystal or nonlinear system of input fluctuations, okay? What mathematicians showed that V can be always diagonalized in some way. So when you make this transformation, this is what you do when you have you change, you apply a transformation, symplectic transformation S on the operators A, okay? Then it gives rise to a symplectic transformation of the covariance matrix, which is this one, okay? So this is what happens when you change, you use symplectic transformation. And it can be shown that it can be diagonalized in some way, so it is diagonal of K1, kappa 1, kappa n, kappa 1, kappa n. But this, it's a, of course, S has as a subgroup the unitary transformation, so the real change of basis, but it, of course, it's just a part of it. And S is much more general than the unitary. It's all the nonlinear effects, okay? And all the nonlinear effects can end up with on a matrix which is diagonal, but this, you see here you have on your matrix, you have K1, Kn, and the same, K1, Kn. Okay, so it's not like the previous one, but the previous one was what I had on operators, okay, transformation of the basis, something like that. Here it's what I have on the covariance matrix, okay, it's another problem, it's related, of course, but it's another thing. Okay, if the state is pure, input state is pure, what does it mean? It means that, okay, I erase my little box. It means that you shine at the input a pure state, okay, so a state which is vacuum and coherent state, for example. And the processing of that is conserve the purity, so doesn't destroy photons or create as added fluctuations, okay? Then in this case, it can be shown that this state is pure, the kappa are kappa are all equals to 1. So my matrix Jag is the identity. So it's very simple. What does it mean? It means that V how do I write it? Simple. Okay, I don't write the mathematics because I have no time to go into the detail, but just the physical consequence of that. Is that yes, I have no time to show you the thing. So I just state it, okay, and you have to believe me. It's okay? I need almost half an hour more to do it right. Is that there exists a base, there always exists. So in the case of pure state, there always exists a basis, a mode basis, in which V is diagonal. What does it mean? It means that there is always a possibility of disentangling. Is it okay? Yes, disentangling things, okay? Which is not at all obvious. So by mode changes, I've shown you that sometimes the 2,0 minus 0,2 by mode change was 1,1. So, okay, so you were able to disentangle in this case, but it's not a general demonstration. Well, it would be a bit surprising that you were able to disentangle any problem, okay? But it is a case in this thing. So symplectic transformation, so linearization of fluctuations, and pure state. Okay, quickly go back to this multi-homodyne detection with some drawings, so it's a bit clearer, I think. So when you want to characterize a single mode state, so let's say, for example, I have a squeeze vacuum like that in a single frequency mode, okay? What do I do to do that, to see if it is squeezed or not? I mix it with a laser beam in the same mode, okay? Same frequency mode. I measure by a bucket detector the two outputs, make the difference, okay? When I scan the phase of the local oscillator, what I do is I rotate the projection of this thing onto the axis. So I will write for phi equals 0, I will see the fluctuations here. For phi equals pi over 2, I will see the fluctuations here. So here I call it x and p, but p is y and y is the same. So it depends on the age of my transparencies. Sometimes it's y, sometimes it's p. Okay, so what you have at the output is fluctuations, of course. What you see are the fluctuations corresponding to that. And when you scan the phase, you have here, you project for phi equals 0 on that extended fluctuation, so you have more noise. And if you now project phi on phi equals to pi over 2, you have the smallest parts here, okay? So your noise changes in amplitude from the two. So this is a proof that your noise is phase dependent, okay? Then you use, instead of just looking at fluctuations, a spectrum analyzer, which transforms fluctuations into a signal, okay? And so you have a signal, which is here, sorry, too fast, which varies from a big value to a small value, big value, small value, according to the rotation of your ellipse, okay? So this is the kind of signal that you expect. And you have to verify that the minimum variance is smaller than the vacuum variance. So vacuum is very easy to get. You just put your hand or something, or a card here or anything, which stops the beam. So it replaces your beam by vacuum. And then you have this line, okay? And when you are below this line, you are very happy, okay? Best values here, more than 10 dB, more than a factor 10 of noise reduction. Meaning that if this one is reduced by a factor 10, of course, the other one is multiplied by a factor 10 or more, okay? So the aspect ratio of the ellipse is 100. So it's an ellipse, but really a very squeezed ellipse, okay? Okay, so this is the way to do it. If I want to analyze a multimode state, I've made a series of measurements, okay? So instead of having just one frequency, I have many, okay? So I have, for each frequency, I will have access, I told you, of the p and y and x components. And if I want to look at correlations, I send at the same time two frequencies and the local oscillator. And then I have the noise on the sum of the quadratures, and I use, as I told you, this relation between variances and correlations, which enable me to measure correlations. Okay, so I have everything. Okay, now I go to the main part of experiments that we are doing for 5, 6 years now, which is to use multimode frequency modes, okay? So, so you know almost everything about frequency comps already, okay, with the different lectures. So frequency comp is nice with respect to this multimode approach, because of course it's a superposition of many frequency modes, okay? So this is in frequency, and in time, of course, it's a train of pulses. And the shape of the pulse is as a Fourier transform of the envelope of the frequency components. Okay, this is very interesting for us. So if you take 100 femtosecond pulses, 100 megahertz repetition rate or something like that, which is a usual mode lock laser that you can buy, you have 100,000 frequency modes. So you have 100,000 degrees of freedom, and hopefully if you put some quantum flavor on that, you have a highly multimode quantum thing. But then the problem is how to do it, okay? How to entangle all these frequency modes. And then if we are able to entangle, how can we use this entanglement? Of course, when you have entanglement, you think immediately to make some kind of quantum computers, okay? And then also it's a good thing to sell to funding agencies so they can have money, okay? But it's more than that, okay? Let's try it. Let's try to make some quantum computing with that. Okay, and the solution to entangle all that is nonlinear optics, and more precisely, parametric nonlinear optics. Parametric Dunn conversion, okay? If I use Chi2 crystal, whatever you like, KTP, BIBO, okay, which is illuminated by a coherent state at this frequency, then you know that it's possible to generate twin photons, photons which are correlated. And here, for example, I assume that this photon is in a given mode 1, frequency, direction, polarization, and the other is in mode 2, okay? So you can easily calculate the transformation, which is equivalent of the transformation that I showed you before. And what goes out of that is a two-mode EPR entangled state. So you get entanglement between the two with that. So remember entangled state, EPR entangled state last time. So it's a state for which the X components are correlated, perfectly correlated at the limit, and the Y components are anti-correlated, perfectly also. And there is no Heisenberg inequality limiting each of one because they correspond to commuting variables, it's not conjugate variable. So this was the origin of Einstein argument some time ago. So everybody uses, not everybody, but a lot of people use a monochromatic pump to do parametric Dunn conversion. In this case, you have just to fulfill the energy conservation. The sum of signal and idler frequency is a pump frequency. So the modes that you are able to entangle are just symmetric modes, so that the sum of this plus this gives the pump, okay? So by using a single frequency pump, you are able to create couples of entangled states, okay? So this is good already. You have a lot of modes involved if you work well. But they are simply entangled in some way, okay? So there are many experiments using that. We want to do more, to have more entanglement, more complicated things, okay, to study. And in this case, okay, that's what I said, we use, as a pump, a non-monochromatic pump, okay? More precisely, we use something which has been also explained a lot here. SPOPOs, synchronously pumped optical parametric oscillators. So one has a parametric crystal which is inserted in a cavity, so it's just an OPO, okay? But this OPO has a cavity whose length is equal to the distance between successive pulses of the pump, okay? So I have not the same nice animation that you had yesterday on the fact that when you shine that here, of course, you create down-converting pulse which goes around here, but the pulses are synchronous with that, so they add, in a coherent way, their effects on the crystal, so they add a nonlinearity effect, okay? So at the output of that, I have still a train of pulse, so because the nonlinearity acts only when there is pump light, so only at this time of the pump, okay? So I have the same repetition rate. So if I go to the Fourier transform, the frequency axis, I have modes, the COM for the input. Of course, I have a COM for the output because of the same repetition rate. The width is not the same. The width depends on a lot of things. Because, for example, if you take just one here, we have already some width here. Okay. So it's more complicated because now you don't have a single frequency as a pump, you have this kind of thing. Okay, you have a pump with many frequency components, and each of the frequency components of the pump gives rise to entangled pairs. Okay, so for example, the central one here entangles these two sidebands. Okay, but this component of the pump will entangle, for example, the same here and another one which is symmetric with respect to that. Okay, so any couple of frequency components here will find a father which is able to create entanglement between these two. Okay, so it's a lot of mixing, let's say. Okay, all couples should be entangled. We will see that more precisely after. Okay, so it's a good start for this multi-entanglement that we need for computing or whatever things. So first we have to work a little bit more on this kind of thing. So this was a paper, it was the beginning of everything some time ago now, almost 10 years. So this is theory. German is Spanish on that. We had another trial of experiment for theory, more detailed in this paper. Okay, so what happens? What we are showing that we are creating at the same time photons in different frequency bands. Okay, so the Hamiltonian, which is responsible to the interaction of all that, will be something depending on creation of two. So L and L prime label the frequency components, the teeth of the comb. Okay, so I will create a photon in mode L and in frequency L and a photon in frequency L prime. Okay, this is twin photon generation, and this will be obtained if I have a pump component at the sum of the two frequencies. So it's proportional to the amplitude of the pump field at the sum frequency. Okay, this is energy conservation. Then, since H has to be Hermitian, I have to add the distraction of the twin distraction of two photons. Okay, and of course, this process depends on the crystal. So, in a way which is phase matching and nonlinearity of the crystal that can put in a chi coefficient depending on the two frequencies. Okay, but what you know is that it is bilinear because it's chi2 effect. Okay, if it is bilinear, it means that you have a matrix. If you put all that in a G matrix, LL prime, this matrix is symmetric also, because when you change L prime into L, you have the same mixing. So if it is symmetric, it can be diagonalized. Not yet, okay. So first, let us look at the matrix. So this is G, L, L, L prime. 100,000 components here, 100,000, it's a big matrix, 100,000 components. Blue is 0, so it's a lot of zeros, which is nice also for diagonalization. So it's sparse matrix. And the values are on the anti-diagonal mostly. The width here is a pump width. The width here is a phase matching width. Okay, then let's diagonalize it with eigenvalues lambda k, okay? 100,000 eigenvalues. And of course, when you diagonalize, you have a unitary transformation which goes from the initial states, which are the frequency single mode states, single frequency mode states. And here we have a superposition of different frequency modes. You have a frequency comb mode, okay? So you have a coherent superposition of different frequencies, which is a comb. In the new basis, the Hamiltonian contains only terms in the diagonal, and on the diagonal you have squares, okay? B squared k, B squared. In front of it you have this lambda k. So if lambda k is equal to 0, this removes the term, okay? And the larger the lambda k, the larger the two-photon creation effect in this mode. So, but now it's creation of a photon in this mode which is everywhere in the frequency spectrum, okay? It's not an eigenstate of energy. So the reason, when you have this kind of squared annihilation and creation operator in a Hamiltonian, one shows that this gives rise to squeezing. This is a squeezing transformation. Okay, so the effect of this Hamiltonian on the input, and the input is what is nothing. You have no light at the subharmonic wavelengths at the input, okay, so it's vacuum. So you have vacuum, and you apply that on vacuum, you have squeezing, okay, directly. So the base for which you have this squeezing that I showed in a general way, here it's just the basis which diagonalizes the interaction, which makes sense. And so at the output, you will have a squeeze state proportional to the lambda value in each of these modes. Okay, if the lambda is 0, you have no squeezing, so you keep the vacuum. Okay, and they are independently squeezed. If one looks at the shape, so it depends, of course, on the matrix. If one takes a simple shape which enables to make analytical calculations, you find modes which are Gaussian modes. So it's a Hermite-Gauss modal amplitude. The one I mentioned, I don't know if you remember the first lecture yesterday morning. I showed that it was a possible basis for pulses of light. Okay, so in the frequency domain, the first one is a Gaussian shape for frequency components. Second one is this one, third, and so on and so forth. So it's in frequency, but you can go in time domain by Fourier transform. And the same, you know that Hermite-Gauss Fourier transform is still Hermite-Gauss. So in time now, it's a pulse which has a Gaussian shape for the zeroth mode, a pulse which has this shape for the first one, and so on and so forth. Okay. So these trains of pulse are eigenstates of the interaction. Okay, this is squeezing, but I don't want squeezing, I want entanglement. Okay, multi-entanglement. But as you know now, it's just a difference of point of view to go from one to the other. Remember, the 1-1 state, factorized state was 2-0 minus 0-2. It is the same here. You can show that if you start from squeeze state in two modes, B1, B2, if you change the basis in the same way as for the 0-2 to 0, so change the basis with plus combination or minus combination of the two modes, then these two are EPR entangled. Okay, so you go from factorized non-classical state, factorized squeeze state, to not factorizable states, okay, which are these EPR states. So you transform the squeezing into correlations, as I tell you, it's the same results, okay? It depends on the way you do it, but it's the same results. So for example, let me take the first two modes that I showed you before. Okay, the first one is Hermite-Gauss like that. The other one is Hermite-Gauss first order. If I add these two, okay, take the plus sign, I will enhance this part and cancel the other part. So I will have more modes on the highest frequency side. And if I take the minus sign, I will have the reverse. Okay, so what are these two modes are entangled, and you see that this one is more on high frequency side, and the other one. So you will have the entanglement between frequency bands, okay? Not frequency components only, but also with light which is in parts of the spectrum. Okay, this is what is expected. Okay, so just to finish with this theoretical part, what goes out of our SPOPO is a factorized set of squeezed vacuum states in a right basis. Okay, so it's and it turns out that it is X squeezed for the first one, Y squeezed for the second one, and so on and so forth. So it's like that. Okay, but this is in the basis of these eigenmodes. Okay, if you look at the basis of the frequency mode, this is the one that we started from, of the 100,000 modes, then it's like that. Okay, I have no other way to show that it's a mess. It's okay. Each wire here it corresponds to a given color. Okay, and so if you try to extract one, okay, you extract everything. You have complete correlations with everything. But okay, so this looks very complicated, but it's the same. Okay, so even each time we want to explain things, of course, we will go to this basis, which is the simplest one. Okay, now experiments. So the center of the experiment is the SPOPO. Okay, so this is the SPOPO, 4 mirrors and a nonlinear crystal in the middle. Okay. It is pumped by a frequency coming from a laser, which is TISAF laser in the red. Part of the light is used to double, okay, so it goes from red to blue. And this blue light, this comb of blue light, is then used as a pump, okay? And then the parametric oscillator will divide by 2 the frequency, almost, I mean. And so it will go back here at the output to the same frequency as the pump, the same area of frequencies of the pump. So we can mix part of the pump with what goes out here. Sorry, so I shouldn't have put it on blue, but in red here. Okay, so this is what we want to analyze, this light going out of the SPOPO. So as you know, an optical parametric oscillator has a threshold above which it oscillates, so it gives light. It turns out when you make all the theory that the best squeezing that you have is below threshold, but very close to threshold, okay? So below threshold means that you have no light out, so no mean field, but you are still modifying the quantum fluctuations of the light, and you are squeezing it. So it's a field which goes out of that has a mean value which is 0, so it's very weak field, but modified, squeezed. Okay, so we are in the right approximation for linearization of things, because the mean field is so small that you can really linearize everything. Okay, now I have to analyze that, and I will do it with multimode homodyne detection. Okay, so one needs here. So this is a mixing on the beam splitter. One needs field here that you can put in many different frequency modes. Okay, and to do that, we use another very nice trick, which has been developed in the last decade or so, even more, which is pulse shaping. Okay. Pulse shaping is something which is related also to SLMs. So it is a grating here, so which disperses the frequency component of the input comb. And then each of these frequency components has a phase and an amplitude which is changed by SLM. Okay, the phase can be changed at will, but the amplitude can only be reduced, not amplified. So you can only reduce the width of the spectral width and not enhance it. Okay, but you can do it a lot by that. For example, you can put the right phases here so that when you recombine the frequency component, you have pulses of strange shapes that you can change at will. Okay, and then this is used as the local oscillator and homodyne detection here. For example, let us take as a trial mode basis the frequency band basis, the Frixel. Okay, so let's take 10 bands in the spectrum. So this is the spectrum of my OPO, spanning over something like 10 nanometers. It's always 100 femtosecond pulses. And I produce with the SLM this kind of band. Okay, so I can select by the SLM a given band, or I can select 2 bands, which is what I need for correlations. Or I can put any other thing, but this is a good basis to start with. Okay, so I do it here. I create these bands and mix it with the output of the system. So this is what we published last year. Okay, so I have 10 bands, so I will have 10 measurements of variances. And then 10 multiplied by 9 over 2, so 45 couples of frequencies to measure the correlations. So total is 55. Here they are, okay? So this is what takes half an hour. So one assumes that the beam is the same during half an hour, okay, which the experience is rather stable, so it's true. So you see that, so these are these homodyne signals as a function of the phase, as always, okay? So for example, this one tells you that you are looking really at a squeeze mode, okay? It goes up and down. The red line is all vacuum state, okay? Vacuum level. So for many of them, you have squeezing here, here. This one is the best. And for others, you have nothing. Okay, no phase insensitive noise above shot noise, above vacuum noise. Okay. So this enables us to have the matrix. The first part of the matrix, and it's good news, is zeros for the part which correlation between the p's and the x's. Okay. And then, oh, sorry. I don't know why, but they should have a lot of numbers here and a lot of numbers here. Okay. It's strange. Okay, so you see that we have been able to measure all the XX correlations and the X variances and all the PP correlations and all the variances, okay? And found experimentally that there was no XP correlation, so the 0 and 0 are experimental, but correspond to the theory. The theory tells you that you have no correlation between the X's and the P's. So it's good news. In 16 bands, we have done it also, so it's even more number of measurements, okay? And now this has not been erased, okay? So this is the different values. So here also the X and the P's are not correlated, so I have a sub-matrix which is X matrix and a sub-matrix which is a P matrix, which are here. Okay, so the diagonal is here, and you have a lot of correlations because it's positive. No, anti-correlation. You see the minus sign here. I have anti-correlation between the x's, and I have here, this is positive. I have correlation between the p's. Good news also. Remember, EPR state was a state for which you have correlations on one and anti-correlations on the other. Okay. So what to do with that? Now we know everything. We have the whole information about the state because we know that the state is Gaussian. Why? Because we start from vacuum and coherent state, and we process it by a symplectic transformation. Okay? So we know it's Gaussian. A Gaussian is completely determined by covariance matrix. We have it. But now we would like to know the physical content of it. Okay, there are different ways to do it. First, of course, we would like to know how much entanglement we have between two parts, two components. Here we have 10 components, for example. So there are, we don't have Alice and Bob, as I told you at the beginning. We have an Alice-Bob beam, okay? And then we can cut it from an Alice part and a Bob part the way we want. Okay, for example, we can cut it on the high part, high frequency, high wavelength part and small wavelength part, but we can cut also these blue lines summed against the red lines, okay? Or any other things. It turns out that there are 511 possible bipartitions of these 10 bands, 2 to the n minus 1. Okay, so we have 511 possibilities of having two parts. And look at the correlation between these two parts. So entanglement can be assessed by what is called entanglement witnesses, so some values which tells you it is entangled. Or so no, here it's sufficient and necessary because it's Gaussian. So they tell you really that it is entangled or not. And the most popular one, it was called the PPT, positive partial transpose criterion. Okay, I don't go into the detail of it, but okay, from the values in the covariance matrix, you can have this witness. It gives you some number, and if this number is negative, so it's below this green line here, it is entangled, okay? The different points correspond to these 511 different bipartitions, okay? And you see that all are below the green line. So all these 511 bipartitions are entangled. This one is more, if we think there is some kind of ranking of the entanglement by this witness, this PPT witness. This one is more entangled than this one, okay? Why not? But let us look at the mode, which is, here they have just been ordered by values of the PPT eigenvalue. Okay, but we can look at what is the mode corresponding to that, what is the bipartition corresponding to that, and what is the bipartition corresponding to the other So this one is the low wavelengths against high wavelengths bipartition, okay? Which makes sense. The most power of the pump is on the center, okay? So this twinning part is dominant in some way, okay? So it cuts into low frequency and high frequency. But this one, for example, which is the least entangled, but still entangled, is center against the wing, okay? And of course, this one is not produced by the center frequency. It was more produced by what happens in the wings, but it's still entangled. Okay, so we have a lot of entanglement. We are happy. But there are not only 2-partite entanglement, can be 3-partite, 4-partite, 10-partite entanglement, which correspond to the fact that we cannot factorize the state in all these parts, okay? Or we can factorize. So it's more complicated to assess, but we have friends, Werner Vogel and his team, Jan Sperling and others in Rostock in Germany, theoreticians, which have a very nice criterion for multipartite entanglement. Okay, so we went there in Rostock and just give them the covariance matrix. And then they worked on it. Okay. So now it's more complicated. For example, one looks at the multipartite entanglement between the 3-partite entanglement between the red, the blue, and the green. Okay. And you see now that you have a lot of possibilities because each one can change in length and position. And then it's 3-partite, and it can be 4-partite, 5, up to 10. Okay. 115,974 possibilities. Okay. With 10 bands. And they have that criterion that works. And the same thing, if it is below the red line, it is multipartite entangled, multi-entangled. And it turns out that they are all, except this one, but this one corresponds to the one-party entanglement, sorry, of course. It's not. So this one is already the second one and all that. Okay, so multipartite entanglement occurs for this more than 100,000 partitions. Okay, so it cannot be more entangled than that in some way, okay? Okay, now, of course, we have the other possibility is to look at eigenvalues, okay? We have this 20 by 20 matrix, so 10 for x, 10 for p, 10, 10, okay? You can diagonalize it for the 2 blocks and look at eigenmodes. So here the eigenmodes are in the frequency domain. This is the weight of each of the frequency band modes, okay? So it gives, in some ways, a shape in frequency domain of the eigenmodes. So you see the first one looks Gaussian. Second one looks second Hermite-Gauss. Third one also very good. It's worse and worse in some way, you see, but because we don't have enough bands first, and also the more the higher the number here, the number of nodes of the thing, the wider the frequency spectrum. And from here, the frequency spectrum of the eigenstate is too wide to be well measured by the local oscillator, because the local oscillator has the width of the laser, the spectral width of the laser, cannot be enhanced, okay? Whereas these modes are broader. So we lose a little bit this effect by our measurements. So we will change that. And the eigenvalues give us a kind of squeezing value of the different things. You see that this mode is highly squeezed, more than 6 dBs, like that, okay? It's a state which is along the p direction with a rather high squeezing value. So it's also good news for the applications. The second one is rather well squeezed also, but then it goes up here. And for the last one, it's not squeezed. Okay, it's just a coherent state. But, okay, we can say that we have something like 11 squeeze modes together. And so the multi-entanglement that we have before is just a result of the projection of this 11th squeezing on modes which mix things, okay? So this explanation, this kind of characterization is more precise, of course, than the entanglement one. Because here we know everything about the mode, the multimode state. Okay, so this kind of thing has been enabled us to measure things for quantum noise, but of course it's not restricted to quantum noise. You can use it, the measurement of multi-homodyne measurement, you can use it just to characterize the noise of frequency comb, whatever it is. For example, a modal laser. So this we have done also. This was the thesis of Roman Schmeissner on that. So it's the same setup, except that we have removed the OPO. Okay. So this is the laser that we want to analyze, commercial laser. One part of the light is processed to have different local oscillator shapes, okay, like before. And the other part should be just the beam itself, but for example, for the phase, of course, the two beams have the same phase. So if you just mix this one with this one, the phase information will be cancelled. So the first thing is to have a passive cavity here, which stores in some way the light during a long time so that it averages the phase. So what you see is the phase difference between this one, which varies instantaneously with the laser, and this one, which is average over the cavity time, okay? And then it's analyzed here. So this is the same as before, except that it's not below the shot noise, but it gives amplitude and phase covariance matrices with positive values everywhere. Okay, you don't have this positive and negative, which is a sign of EPR, and EPR is quantum. So, okay, but we have a lot. It's in dB scale. We see that we have a lot of excess noise or in big correlations in the system. Here also, what is interesting is to extract eigenmodes, noise modes of the laser. We can extract modes from the amplitude part or from the phase part of the thing. And further, what we can do is to analyze these modes as a function of the Fourier component of the noise, okay? Because the spectrum analyzer gives you the noise component at a given noise frequency, okay? Usually we work in the megahertz range, but we can change this frequency. Look at low frequency fluctuations here, so 100 hertz, or very high frequency fluctuations, megahertz fluctuations, okay? And you saw in the dB scale here, there is a dominant eigenvalue here, okay, which is 3 times, 4 times bigger than all the others. You see that the noise itself, so the amplitude of the eigenvalue is very large for low frequency, and then tends to a value which is 1, and 1 is short noise. It's a vacuum noise. Okay, so at high frequency, you have vacuum noise, which is expected. Okay, it's only at low frequency that the dynamics of the modal laser enters into the game and gives this noise. Okay, and this one is for phase, and for phase it's even more stringent that you have 10 dB, something like that, more for factor 10, more for the eigenvalue for the first mode than for all the other ones. Okay, you have dominant noise mode, which is called the principal mode. As far as the shape of these eigenmodes are concerned, you see that the first one, so for amplitude noise, you have this shape. Okay, we're not going to the detail. Perhaps it's more interesting to look at the eigenmodes for phase. You remember the first one was really dominant, and the first one is this one. It has almost the same projection on all the components, meaning that it has the same shape as a mean field. So the dominant noise mode is a mean field mode in some way. And this tells you that you can write things like that. So the field is a mean field times a phase noise. Okay, and this usually people write that directly for any laser, so that the laser has a fixed amplitude and only varies in phase. So here we justify this kind of approximation, and we see how good it is or not looking at the other eigenvalues. So this was, I think, something that interested the people in modal laser as a very detailed analysis of the noise in the system. Okay, last part.
Of course, we would like to use this highly multimode entangled state in one way or another to make calculations or quantum processing effects. So we began, as always, by making a little bit of theory and then looked at what is possible in the experiments. So quantum computing, of course, I have 6 minutes remaining. I will not cover all things of quantum computing, just give you some flavor where we are now. There are different architectures for quantum computing. The most widely used one is the one which is just a transfer from classical computing to quantum computing, which is the fact that you enter in different registers, different wires in your computer, and then you process this information by gates, okay? And you have gates, successive gates. And just in quantum computer, you replace the classical gates by quantum gates, okay? Gates obeying quantum rules, but it's the same. And then at the output, you have your answer. So this is not something which is well adapted to what we have, because we have this big state which is there. Okay, it's a quantum, but it's not something that you can process in parts. But there is another architecture which has been developed in theory and a little bit in experiments for very few numbers of modes, which is what called measurement-based quantum computing, or one-way quantum computing. It starts from a very complicated quantum state and highly entangled quantum state, which is called cluster state. Perhaps you have heard of this name. A cluster state is a state which can be written and drawn in this way. So each green point corresponds to a node of the network, but in our case, it is a mode of the system. Okay, it's a degree of freedom. So each one is a F1, F2, F3, and all that kind of things. And then the red line corresponds to entanglement, to correlation. So the twin photon generation generates twin photon in this and this, or in this and this, or in this and this, but not in between this one and this one. And so there is a topology of the cluster state. Okay? So it corresponds to a given Hamiltonian, interaction Hamiltonian. Okay? So the way to process the calculation is that you put your question, your input state somewhere on a node. Okay, you report it here, and then you measure things on the different quadratures of the different nodes. Okay, you measure things which depend on this input and depend on the way the system are correlated. Okay. Then you have at the output at some other node some state, and you process what you measure on this according to what you have measured before. So it's the response at the end depends on the series of measurement results that you have obtained before. This gives you information that you apply to this end thing, and the result of this application is the answer. What is an answer in quantum computing? It's just the effect of evolution. Okay, so you are able, by doing that, to apply any transformation on any input state. Okay, and in particular, quantum gates, which allows you to factorize numbers or whatever. But we are not at the point of factorizing 100,000 numbers of on 100,000 digits. But this is our hope. Okay, so first thing is to be able to create these cluster states. Okay, is our system a good start for that? This is where we are now. For example, this 4-node cluster state is a popular one. It has been shown that it is produced from 4 squeeze modes, independent squeezing, by a linear transformation. So this is a basis change that you apply to the squeezing, and then gives you entanglement, the right entanglement that corresponds to this kind of topology. So people do that usually. For example, this is something coming from Furusawa group in Japan. So they produce 4 squeeze states by 4 different single mode systems, okay, on the table. And then they mix it with beam splitter and phase shifts in order to mimic that.
And they have output modes, and then they look at the correlations to the output modes. In our case, we have all that in the same beam. Okay, so we just have to do that, and that is just a change of basis. Okay. So if you want to produce these cluster states from our states which are squeezed, which are these ones, we have to process this matrix on that, meaning that this one is also a mode change with respect to the bandwidth. If I make the product of the two matrices, I have this big matrix applied on the modes, on the frequency band modes. It's complicated, but it can be implemented on our pulse shaper. Just a matter of some lines of computing. Okay, so the cluster states are there. They are. This is spectral. Here it's spectral. Yes. Okay, these are the spectral components, one by one, and here it's frequency bands, the one that I have in my experiment. Okay. So the cluster states are there. We can just looking at the covariance matrix that we have, when making this kind of transformation on it, we can extract the information relative to the cluster. Okay, there is much more than this cluster in the system, but we can check if there exists the correlations related to this topology of clusters. And we found yes. Okay, I will not go into the detail, but we found that really we have the same correlation that is needed to create that. The only difference is that theoreticians assume that you have perfect squeezing on the nodes, because they are theoreticians, and we don't have perfect squeezing. Of course, we have 4 or 5 dB, things like that. So if you want to make quantum calculation with that, perfect squeezing is okay, and quantum calculation for non-perfect squeezing is another thing. Okay, we have to make error corrections schemes and things like that. So, but it is always the way it is with experiments. Okay, you have defects. We are not exactly corresponding to theoreticians. But we have seen many other clusters, all these. So all this topology means different kinds of entanglement. And since we have almost all possibilities of entanglement, we have in particular all these ones that we checked also. But we don't have to change the experiment. We just have to change the way we process the data. All these clusters exist in the beam, but in order to have the processing that, I have to be faster, now to have the processing which is needed to making one-way computing, I cannot destroy. I cannot wait half an hour measuring all the covariance matrix elements. I have to process the same state. Okay, I measure the state, so I have some state reduction and more, but it's the same one that I have to do it. Here, a homodyne detection destroys the beam. If you make one homodyne detection, finished. But the only thing that you can do is to measure everything at the same time. And this we can do, that I've shown you before, by replacing the bucket detector homodyne detection by multiplex homodyne detection. Okay, so this I showed you before. Instead of just mixing your beam to measure with local oscillator and looking at intensities in both sides, you first disperse the light, measure the different frequency components, and have here the information. For example, we had 6 detectors in the experiments. We have these 6 bands. And if you measure, you record the fluctuations on the first band, second, third, and all that. And in order to get the covariance matrix, so all this is recorded at the same time on the same state. In order to get the covariance matrix from it, you just look at the height of the fluctuations, which gives you the diagonal element, the variance. And if you want to have the correlations, it's what I said you before, you just look at the product. You make the product time by time, equal time here and here of the fluctuations and average. And you have the off diagonal. Okay, so everything comes in the same thing, but also, as I told you before, you cannot measure the 2 phases, the x and the y's at the same time, because you have to choose a phase on the local oscillator, and this fixes if you measure x or y, and not both. But for most cases, it's enough. Okay, you cannot make all the quantum computing operations with that, but you can make a lot. So just to show you that it works, so you can diagonalize from this information, and you find the same states. Okay, but with a lower resolution because you have only 6 frequency bands instead of 16. And also, it was possible from this information to extract cluster states, and they were a little bit less squeezed than the previous one, but still they are in the non-classical states. Okay, so I finish, yes. So the system that we have built is able to produce highly entangled quantum states that we can call WDM, so just for commercial. So it's the same wavelength division multiplexing that is used in fibers for communications, but for us, we have added quantum flavor in it. Okay, this is, as I told you, frequency basis is a mess, but we are able to simplify the mess by looking at the things in the right basis. Data processing reveals the cluster states, so you need only to mix your data in the right way to get the answer. And you have seen we have 6 bands in the one case or 16 in the other. Of course, there is no limitation other than just the number of Ys that we are dealing with and the fact that we have to put everything in the same thing. So it's scalable, easily scalable, just technical problems to more frequency band than that. Not to 100,000, which would be the ultimate thing, but 10, 20. So theory tells us that there is at least 20 squeeze modes, or even 30 squeeze modes in the system, highly squeezed modes. So we don't see this highly squeezed thing because of detection is not perfect. So we hope a good thing. And now we are investigating how we can use it for some kind of real quantum computing operation. And the one we are considering now is secret sharing, quantum secret sharing. So you have some information that you don't want somebody else to know, but that you can give partly to different people so that when they go together, they recover things. So each one has no information about the secret, but several ones have, okay? Something which has been already done, but we expect to be able to share the secret among more people using that. Okay, I stop here, just showing the team in full action. So working hard, as you can see. It's not always like that in the group. And I would like to stress the role of Nicolas Treps, who is co-leading the group with me. And also Jonathan Roslund here is a postdoc. He will leave us, unfortunately, next week. He's a wizard of spell shaping. So this is the one which is able to create all these things and change quickly from one to the other. And he was very effective, and also all the others. Okay, thank you for your attention.